9:47 on a Tuesday night. The roast came out 12 minutes ago. It sits on the counter, resting under foil. The oven door is propped open, and the steel inside is still ticking as the cavity contracts. On the floor of the oven, 3 brown streaks where fat ran off the rack at 200 degrees Celsius. Right now, while the interior holds at roughly 60 degrees, those streaks will lift with a damp cotton cloth in under 90 seconds. In 48 hours, the same residue will need a chisel. The fat does not know what year it is. That 90-second window is the entire story of this video. Inside it, the cost of a clean oven is 0. No detergent, no spray, no gloves. Outside it, the cost is a $15 can of sodium hydroxide and an afternoon. The price of catching the window is 2 minutes of attention. The price of missing it is, at minimum, 20 times that, every time. This is what the Japanese kitchen has known in working practice for at least 100 years. It is also what a chemist at the Massachusetts Institute of Technology described in cold molecular detail in 1882, and what was almost immediately displaced by something more expensive. 1. The 48-hour window. Return to the same kitchen on Thursday morning. The 3 brown streaks are still there, but darker, slightly shrunk. They no longer wipe. A fingernail across one of them produces a thin, hard scrape, like dried lacquer. Hot water does nothing. A damp cloth glides over the top without lifting anything. The grease has changed state. Chemically, it is no longer fat. What happened in those 48 hours is a slow molecular process called oxidative polymerization. The fatty acid chains in the original spills, sitting on hot enamel and exposed to oxygen, gradually formed cross-linked bonds with each other. The same reaction, in a much faster version, cures linseed oil into a hard finish on wooden furniture. In an oven, it produces something closer to a low-grade varnish welded to the metal. Take a single drop of cooking oil and place it on the floor of an oven at 200 degrees Celsius. In the first 30 seconds, the triglyceride drop heats and spreads into a hot, thin, transparent film. A damp cloth at this moment lifts it cleanly. Over the next several minutes, a fraction of the chains undergo thermal hydrolysis, heat-driven cleavage at the ester bond, producing free fatty acids and glycerol, still water-soluble. Past about 30 minutes of continuous exposure, 2 slower reactions take over. The first is oxidative cross-linking. Oxygen inserts into the carbon backbones of adjacent fatty acid chains, forming peroxide bridges that decompose into stable carbon-carbon bonds between chains. The film thickens, loses transparency, begins to repel water. The second is carbonization, the slow stripping of hydrogen and oxygen from the backbone, leaving elemental carbon embedded in the polymer. The color shifts through yellow to brown to black. What was, an hour earlier, a soft yellow film now has the chemical character of a thin layer of low-grade asphalt. Hydrogen-bonded networks have been replaced with covalent cross-links. The water that lifted the drop 60 minutes ago can no longer wet the surface. Now the temperature drops. The cavity cools toward room temperature. There is a narrow window, roughly 60 to 80 degrees Celsius, where the polymer is still soft, where uncross-linked fragments are still mobile, and where a thin film of warm water can wet the surface enough to lift the loose top layer. That window is the entire technique. Get in the window, or pay later in chemistry. 2. Ellen Swallow Mitt, 1871. Begin with a name and a year. Ellen Henrietta Swallow, 28 years old, born in Dunstable, Massachusetts in 1842, tutored at home and at Westford Academy, then working as a tutor and house cleaner for several years to save the $300 she needed for Vassar College. She graduated from Vassar in 1870 with a chemistry degree, the first American woman to receive one. She then applied to every industrial chemistry lab in the country. Every one of them turned her down. At the suggestion of one of the chemists who had rejected her, she sent her credentials to the recently founded Massachusetts Institute of Technology in Cambridge. On December 14, 1870, the MIT Corporation voted to admit her, but only as a non-matriculated special student, and only on the explicit condition that her admission established no precedent for the general admission of women. She was charged no tuition. She believed at first that the waived fees were a kindness toward a poor scholar. She learned, years later, the real reason. In her own words, the president of the institute wanted to be able to say, if any of the trustees or students made a fuss about her presence, that she was not a student at all. Her enrollment could be officially denied. Ellen Swallow walked into MIT in January 1871 anyway. She graduated with a Bachelor of Science in Chemistry in 1873, the first woman ever to receive an MIT degree. She married Robert Hallowell Richards, the Institute's professor of mining engineering, in 1875. Their wedding trip to Nova Scotia, 3 days after the ceremony, was accompanied by Robert's entire mining engineering class, who had been invited along. This is the woman who wrote The Chemistry of Oven Grease. Three. The 1882 Manual. Nobody reads. In 1882, Ellen Swallow Richards, by then a faculty member running a woman's laboratory she had personally helped fund out of her own salary, published a small manual, co-authored with her student Marion Talbot, titled The Chemistry of Cooking and Cleaning, a Manual for Housekeepers. Estes and Laureate, Boston, about 90 pages. It contained, in the dry, technical voice of a chemist who had never been allowed to be sentimental, the molecular logic of the American kitchen. Stain removal as acid-base chemistry, bread leavening as carbon dioxide release, silver tarnish as sulfide reaction. And in several chapters that have, in the intervening 144 years, almost entirely faded from public memory, the precise treatment of grease. Richard's working position, stripped to its essentials, can be stated in 3 sentences. Animal and vegetable fats are esters, 3 fatty acid chains joined to a glycerol backbone. Fresh, at low temperature, they are mobile and easily emulsified by warm water and a mild alkali. Exposed to high heat across repeated cooking cycles, they polymerize and carbonize, and only then do they require strong reagents. Clean before polymerization. Use temperature first. Reserve harsh substances for the worst case, not the default. Her work earned her a permanent appointment as instructor in sanitary chemistry at MIT in 1884, a position she held until her death of a heart attack in March 1911, while still actively conducting research. She had been a member of the faculty for almost 40 years. Smith College had granted her an honorary doctorate the previous year. MIT had still not granted her any advanced degree at all. 4. What was lost? There was a generation of cooks on both sides of the Pacific who understood this without ever opening a chemistry book. They wiped the stove and the oven while it was warm. They folded a cotton cloth into quarters and used each quarter in turn. They never wrote it down because it was not the kind of thing that needed writing down. It was the way the kitchen ended every night. In our generation, they stopped. What replaced them was a chemistry and a business model. Both deserve to be named. The chemistry is sodium hydroxide, lye, the same compound the Egyptians used in mummification. It dissolves grease by attacking ester bonds directly, true saponification, the strong base hydrolysis that turns triglyceride into soap and glycerol. At a pH of 14, it is also strong enough to dissolve human tissue, which is why every can of commercial oven cleaner is printed with warnings in the voice of a workplace safety officer. The chemistry works. The objection is not that it doesn't. The objection is that it is being asked to do a job that, inside the 90-second window, warm water alone can do. The business model is more revealing than the chemistry. Sodium hydroxide as a raw compound cannot be patented. It has been industrially produced since the early 1800s. But a specific formulation, combined with surfactants, foaming agents, and stabilizers, packaged in an aerosol can and registered under a brand, can be. That formulation gets market exclusivity for 20 years. 20 years of exclusivity justifies a marketing budget. A marketing budget pays for television commercials, magazine inserts, product placement, and shelf space negotiations with retailers. The cycle pays for itself year after year. A damp cotton cloth pressed against warm steel does not enter that cycle anywhere. Neither does a half cup of sodium bicarbonate from a yellow cardboard box that has cost roughly the same, in inflation-adjusted dollars, for over a century. Neither does sodium carbonate. There is no patent on water. There is no recurring revenue model for a piece of cotton. There is no marketing budget for a behavior that costs $0 and lasts 90 seconds. So the technique did not lose a debate. It lost a market. No one buried it. No one had to. When the marketing dollars on one side reach into the hundreds of millions per year, and the marketing dollars on the other side are exactly zero, the curve of consumer awareness bends in only one direction over a generation. The cheaper, gentler, equally effective method drifts out of public memory, not because anyone hid it, but because no one was paid to remind anyone of it. This is something colder than a conspiracy. Economists call it market drift. It does not require malice. It only requires asymmetric advertising budgets across 2 generations. 5. What the Japanese household kept. Which brings the camera back to the Japanese kitchen. The Japanese household, broadly speaking, never went through the same forgetting. Not because of mysticism and not because of any single ancient secret, but because 2 ordinary, well-documented habits stayed inside the everyday routine of cooking. The first is the principle the Japanese call tsuide-ni. It translates as, while you're at it, and it describes the practice of attaching small cleaning actions to existing rhythms. While the kettle boils, the counter gets wiped. While the oven cools, the inside of the door gets wiped. The behavior is not framed as a chore. It is framed as part of cooking itself. The second is a piece of equipment, the fukin, a small square cotton cloth traditionally folded into quarters and used on each face in turn before being rinsed. Not paper, not disposable, not branded. Often hand-sewn from worn-out towels. It is the simplest tool in the Japanese kitchen, and it is what makes the 90-second protocol practical, because the fukin is always within arm's reach at exactly the moment a warm surface needs attention. There is a wider cultural frame around these habits, references to Shinto purification, to Zen monastic sweeping, to the proverb tatsu toriato wo nigosazu, dated to at least the late 1500s, meaning roughly, a departing bird leaves no muddied water. Whether those framings do real causal work, or whether they are simply the cultural skin around 2 practical habits, is an open question. What is not open is that the habits themselves are concrete, documented, and chemically sound. The technique does not require Japanese culture, it requires the cloth and the timing. Both are universally available. Neither has been advertised to anyone in living memory. 6. Level 1. The fresh wipe. Now the protocol, in 3 levels of severity. Level 1. The oven used tonight. Wait approximately 15 minutes after switching off the heat. Touch the outside of the door when it is dropped from hot to warm but not yet to cold. The interior is somewhere in the 60 to 80 degree range. This is the window. Fresh triglyceride spills exist as soft, low-viscosity liquid. They have not yet polymerized. They have not yet bonded to the porcelain enamel. Take a folded cotton cloth, kitchen towel, dishcloth, or, for the closest match to Japanese practice, a small square of plain cotton kept for this purpose only. Run it under warm tap water. Wring it half dry. Wipe the floor of the oven, then the walls, then the inside of the door, avoiding the heating element. The cloth should pick up the residue without scrubbing. If real scrubbing is required, the window is missed. Total time, including the wait, under 2 minutes of active attention. Cost per use, effectively zero. Chemicals introduced into the kitchen, none. This is what the title of this video refers to. Seven. Level 2. The overnight paste. Level 2. The oven that has not been wiped in months. At this stage, the polymerized layer is partially hydrophobic. Plain water cannot penetrate it. This is the case where most internet recipes recommend a baking soda paste, and where the recommendation is correct, but the explanation is wrong. Half a cup of sodium bicarbonate is mixed with water into a thick paste, applied across the interior surfaces, and left undisturbed for 8 to 12 hours. Most articles will say the baking soda saponifies the grease. It does not. Sodium bicarbonate has a pH of about 8.1. True saponification requires a pH around 13. Baking soda is, chemically, far too weak. What actually happens over those 8 to 12 hours is slower and more subtle. The water in the paste migrates gradually into the porous structure of the polymerized layer, disrupting the local hydrogen bond network and softening the matrix from the inside. The mild alkalinity of the bicarbonate emulsifies the free fatty acids that have already cleaved off the original triglycerides, the easy targets. And as the paste dries at the surface, a fraction of the bicarbonate converts to sodium carbonate with a pH closer to 11, which begins to do real chemical work on the weakened residue. In the morning, the dark brown crust scrapes off with a damp cloth and a wooden or silicone spatula. No lye, no respirator. The active ingredients cost roughly 5 cents. The active mechanism was time, water, and the slow chemistry of a mild base. There is no patent on going to bed. 8. Level 3. Washing soda. Level 3. The oven that has been ignored for a year, or that has had something catastrophic spilled in it, or that has come with a house unloved from a previous owner. For this case, baking soda is not strong enough. There is a second, related, almost forgotten compound sitting one shelf away in the laundry aisle of most American supermarkets: sodium carbonate. Washing soda. Soda ash. Formula Na2CO3. It is what every household in the 19th century actually used for serious cleaning: laundry, floors, ovens, grease traps, before commercial detergents replaced it in the 1950s. Washing soda has a pH of approximately 11.5. It is genuinely strong enough to saponify free fatty acids and partially weakened triglycerides, the real chemistry the baking soda was incorrectly credited with. It is also still mild enough to handle with rubber gloves and a sponge. A pound costs around $2 and will last most households more than a year. The packaging, a plain yellow cardboard box, has barely changed in 80 years because no one has had any commercial incentive to redesign it. Spread a paste of washing soda and warm water across the worst spots. Leave for 2 to 3 hours, not overnight. The higher pH means it works faster. Then wipe with a damp cloth. The carbonized layer lifts in dark, lacquer-like sheets. Rinse with warm water. Repeat once if needed. This is not new chemistry. This is the chemistry of every household on either side of the Atlantic until somewhere around 1955, when the marketing budgets came in. A note before the limitations. The video can give you the technique, the blueprint PDF, accessible right now by scanning the QR code on screen, gives you what video cannot. A printable one-page kitchen card with all 3 levels. A pH and temperature chart for the 3 compounds. A sourcing guide showing exactly which box on which supermarket shelf in the United States, the United Kingdom, the European Union, Japan, and Vietnam contains genuine sodium carbonate. A field test log template so the experiment can be tracked rather than guessed at. Excerpts from Ellen Swallow Richards' 1882 manual, with the chemistry pages laid out so the original phrasing is visible. No email, no sign-up, no upsell. The QR code stays on screen for the next 30 seconds. The blueprint is free. If this video disappears from the platform tomorrow, the PDF persists on the phone of anyone who scanned. End callout. Now, 3 honest limitations, none minor. All reasons to keep 1 can of conventional cleaner under the sink for genuine emergencies. Used carefully, used rarely. First, sugar carbonization. Caramel that is burned at high heat, the pie that overflowed, the syrup that boiled over, forms covalent bonds with metal oxides that mild alkalis cannot break. For that specific case, a small, targeted application of true sodium hydroxide cleaner is the right tool. The point is not that lye is evil. The point is that lye is being asked to do everything when it should be doing one job occasionally. Second, do not mix the steps. Spraying vinegar onto a baking soda paste produces impressive foam and almost no useful chemistry. The 2 compounds neutralize each other into sodium acetate, water, and CO2 gas. The fizzing has a mild mechanical lifting effect on already loose particles. It has no chemical cleaning effect because both ingredients have been consumed in the neutralization. Use each compound separately. Third, aluminum oven racks should not be soaked in washing soda for extended periods. The alkali attacks the protective oxide layer and dulls the surface. Stainless steel and chrome-plated steel racks tolerate it well. Back to the kitchen. It is 9:47 on a Tuesday night. The roast is on the counter, resting under foil. The oven door is open, and the steel inside is still ticking. The 3 brown streaks on the floor of the cavity are still warm. The cotton cloth is in the drawer beside the sink. The whole operation, from standing up to sitting back down, takes less than 2 minutes. That is the experiment. Try it once, this week. Do not redesign the kitchen. Do not buy anything. After the next thing baked in that oven, wait 15 minutes, wet a piece of cotton, and wipe the floor of the cavity. Then, come back to the comments under this video and write what happened. What lifted? What didn't? What surprised you? Photographs help. Honest negative results help more, because the cases where the technique fails are exactly where the next viewer needs to know the limit. The comments below, taken together, will be more useful to the next household watching than every paid review of every commercial oven cleaner ever published, because no one in those comments is being paid to lie about the result. Ellen Swallow Richards wrote 90 pages in 1882. 144 years later, somebody is reading them. Tonight, your oven.